I just wanted to give a very breezy walkthrough of some really work I did several years ago with Jeff Carson, and then Kathy Gillis, Lawrence Coogan, and Abigail Barker and I were postdocs at the time, actually, and that's an expedition to Pedo Deep. And then give just one or two slides about the Atlantis Massif, and then talk about some both older results that Chris was pivotal in kind of making us all get into in the Cayman Trough, and we've heard a lot about it. And there'll be some results from a James Cook cruise in there, and then the most recent seismic data that is just published this week. We have some in an article in Nature Geoscience by Ingo Gravemeyer, and there's two other previous papers. And it all sounds a little bit disconnected, but it's not, I assure you. I want to thank NSF. All of this work I was involved in was funded by NSF, and then where I work now is the Institute for Geophysics at UT Austin, which is some of your Europa people know of. But actually, I kind of have maybe a prosaic point, but I think given the conversations of the last few days, I think it's worth making. That if you think about a mid-ocean ridge, and I'd be curious how much we think magmatism is really playing a role in these ocean worlds, but these very cartoony pictures we like to draw. Green is kind of how we picture the mantle, blue tends to be how we picture the gabbroic lower crust, and this gray is the sheeted dikes. These are the intrusions of basalts that come out of the deeper mantle melt and then flow onto the surface to make the lavas, and then it tends to be draped by sediments. And when we think of our big black smoker systems on, say, an East Pacific rise type, hot, fast, magma-rich setting, it's generally in this very narrow axial region above an axial magma chamber. And the things Andy Fisher was talking about are kind of off on the axial flanks or even in the abyssal plains where there's some topographic gradient. And this is a much more complicated setting. This is when we get to slower spread, less magma-rich, colder settings. This is a cartoon from Henry Dick's work, published in 2008. And immediately you can notice the seafloor is more irregular. A lot of green comes to the surface of the Earth, so we start thinking of this serpentinization going on all over the seafloor. And patches of blue are where there's magmatic intrusion into the lower crust, and then the dikes. And hydrothermal vents like TAG that Jeff pointed out make up these deep rift valleys. So these are very different settings. They kind of make up some kind of end member. There's a lot of papers written about that. There's plenty of details in there. But the point I want to make is that these basalt flows on the fast-spreading axes bury a near-axial fault system that forms right under that volcanic rise, if you will, or that axial rise. And when we look in submarine exposures and geophysical images, we see evidence of faulting that is preserved in the subsurface. And I'll show you pictures of those from the micro to meter scale. And then the second point I want to make is that the detachment faults that pull up these mantle rocks from depth are very visible on the seafloor. I'll show you examples, and they make beautiful striated images, including places like Venus, we think we see them. But that really contrasts with what is going on in the subsurface. When we look in the subsurface, we get a different picture, and I'll show you that. And so I think actually it's fun giving this talk, because if I think back to 13 years ago when I was first exposed to these problems, we've actually made progress. It's sort of hard to see right at the moment. So it's been fun putting this talk together. I'll go quickly through this. This is just sort of your Bible study of axial magma chamber work. Back in 93, sort of 80s, early 90s, Dietrich at Woods Hole and others. This is Graham Kent's paper from 93. It's hard to see that. There's a little black dot on the screen that's about 1 kilometer across, and that's the event that was recorded in an active source seismic reflection data on the Southeast Pacific rise that is the top of this axial magma chamber that actually has melt in it. Things are spreading away from this axis very quickly. The full rate is 120, 130 millimeters a year. Back in the Miocene, it was as much as 200 millimeters a year. And Jeff Alt, after drilling hole 504B in around the same time frame, late 80s, early 90s, found there was a very stepwise change in hydrothermal minerals. The top had very low temperature hydrothermal minerals, clay minerals, very poorly crystalline micas. And then down here, there was a step to amphiboles and very kind of essentially a metamorphic assemblage. And so he basically drew arrows and said there's some reaction zone, and seawater gets pulled down and then it gets popped back out, and that explains everything. And we still, this is a Nature paper from 2014 with the most sophisticated three-dimensional numerical modeling, and it's essentially saying the same thing. There's more kind of instabilities that develop, little shoots. And there's all sorts of interesting things that happen along isotherms, but it's essentially still following that kind of 15 to 20-year-old vintage view of an axial magma chamber, steep isotherms, and this kind of driving this axial flow. So before I go on, I'm going to start showing you some geology and some seafloor images from Jason and Alvin, so we can actually get out to sea a little bit together here. But remember that what we look at on the seafloor, this is just taken the other day. We just took this off the CBS News website. Hawaii is draping the surface of Hawaii. Kilauea is draping the surface of Hawaii with these flows. And Iceland, you can go to the western fjords and you can look at, basically there's a kilometer or a kilometer and a half. This is, a few hundred meters high, but you can see, how do I manage that one? Anyway, I'll keep talking. You can see that those flows just basically drape over the surface. And, the East Pacific rise, is not, as Scott White can tell you, there's similar sorts of things can happen. Here's the rise. This is just taken from the GeoMap app tool, online tool from Lamont, and you can see that within about a kilometer of the East Pacific rise, you basically have a complicated system of volcanic flows that cover the surface and kind of funny bathymetry created by that volcanic construction. And you really have to get out. This is a 6-kilometer scale bar. You have to get pretty far away before you start seeing the abyssal hill bathymetry that is actually a response to the flexure and seafloor spreading away from the ridge. So, and even though these are very prominent distinctive features, these abyssal hills, it's not clear what they are in terms of faults. For example, in Shosho Han's JGR paper last year from the Wanda Fuca plate, just took this right out of her paper, you can see these lines are highlighting these reflectors that are buried underneath lots of lavas and sediment. Again, these are not the abyssal hills. There's a great deal of faulting in the crust that is not expressed at the seafloor. And a lot of times we really don't know what it is or exactly when it formed. So moving on, in 2005, I went with Jeff Carson and others, and there's been a more recent cruise there that Chris German was involved in as well. So there could be some new observations relevant to this faulting issue. But basically, it's on the edge of the eastern microplate, and it rips open a hole in the Pacific crust. And if these are the abyssal hills that formed at the mid-ocean ridge, you get these kind of cross-sectional views into the deeper oceanic crust. And it's a hadal zone, actually, Tim. This is 6,000 to 7,000 meters deep at its depth. And I think the Spanish or somebody dredged some peridotite a million years ago. But we basically concentrated on these crustal sections. So just the one seagoing picture, I wish later I had one. I forgot to put one in our OBS cruise, but at least you can see the deep submergence vehicles. And this is just an example of the kind of work we did. I'm still pretty proud of it, even though it looks rather sketch-like, because it's pretty hard to do. I mean, this is 5,800 meters down. Sorry, this is an XY coordinate system, and this is basically a contour of the base of the lavas. So we're looking around 3,400 meters down below the sea surface, and essentially looking along an area where the base of the lavas drops down. And when we go and inspect that area and kind of do sort of field geology on the seafloor, we find things like this, where there are dikes that dip off to one direction and dikes over here dip off to another. And there are these zones that are a few meters wide, and they're filled with hydrothermal minerals. And when we take samples of them, they look kind of like this. We get quartz, sulfide grains, ground up phyllosilicates and amphiboles. And when we do things like titanium quartz thermometry using mineral compositions, we find that a lot of this veining coincided with the black smoker conditions of a deep hydrothermal system. So this would be like the subsurface quartz dropping out below some kind of hydrothermal vent and chewing up and destroying bits of very high temperature metamorphic systems. This is kind of an amphibole plagioclase estimate, obviously not very precise, but we can basically say it's a very high temperature grain that was then plucked from its rock parent and caught up in this quartz cemented breccia. So this is essentially proof positive of kind of the null hypothesis that this was a fault that was a conduit for large amounts of hydrothermal fluids. And one of the, if there was a surprising thing that came out of this, it was that when we started looking in detail, both at a lot of geochemistry and mineralogy that I published, and then Abigail Barker pursued the strontium isotopes of the quartz, we did find that this blue dot is essentially the composition of those quartz breccias, and it sits in this kind of mixing line in strontium 87-86 ratios between the recharging seawater and the discharging fluid. So this ratio here being that discharging seawater and this being the recharging. So what we're basically finding is that these fault rocks sit and equilibrate with waters that are being pulled down right into the zone of faulting and then spat back out into the black smoker system. So a bit different from the Jeff Alt view of these kind of large circular cells. We have these very localized exchanges. And just some sort of food for thought, Will Wilcock back in 2004, when trying to model seismicity and temperature anomalies, actually imposed those boundary conditions of a fault sucking fluids in and spitting them back out, and found he could account for the thermal anomalies and the seismicity with that kind of assumption. So when we were talking about rheology the last few days, I think some of these events can show how on Earth we can look at venting and kind of infer some crustal strength issues in terms of the lithostatic and hydrostatic pressure, and also the kinds of permeability changes that we associate with this process. So it's all kind of analytical sort of estimates of these events. So everything I was talking about was basically trying to use some geological inference and observation on fluid flow and geochemical exchanges in this volcanic area. It's just a sort of last note about these fast spreading systems, is as you go out here, we know that in the rocks we sampled, we did find a lot of these kinds of features. So this would be a zone of cracking and fracturing where there's a 10 micron scale bar where we found open porosity. And this is kind of a corinthite phase, or magnesium low-grade silicate. And so we know that there is this kind of environment in there as well, and perhaps that didn't form in the same kind of deep hydrothermal conditions. There's this kind of polygenic history of opening new pores after we formed those hydrothermal discharge systems. So moving on to these slower spreading centers, if we look at these detachment faults, like they're very conspicuous. So this is the big difference between the East Pacific Rise, say, and the Atlantic or the Cayman, is just the seafloor. And I think from a planetary perspective of predicting seafloor structure, it's worth kind of considering the different environments, because here you get these deep rifts and these high massifs, sort of Mount Everest scale features, whereas the East Pacific Rise, for example, it's this kind of broad volcanic and thermally buoyant edifice. And there's a lot of recent work bringing AUV data to these detachment fault systems, where we see these corrugated surfaces. Here's one on Venus, actually, that John Spencer, who first found these things in 2001, identified. But we see a lot of these around. And the old idea for a long time was that they are mantle that was exhumed, and during the exhumation was frictionally ground up to make those corrugations. Well, I'm speeding up because I want to get to something really interesting at the end, so just have patience with me. But when we drilled into one of these systems in 2005, the same year we went to Peto Deep, this is sort of the old story of the Atlantis Massif. Lost City Field is there. We found 1.5 kilometers of gabbroic magmatic units that were formed, and preciously little of the mantle rocks below. So in fact, there's very little exhumed mantle in these large, deeply exhumed massifs with fault surfaces. Going to Cayman, we had the same question. We just heard Jeff Seawald talk about this system, the Von Dam field here. Well, it got us to thinking, what's under that? And we decided to shoot some seismic. We did passive source OBS seismic tomography, because we wanted to know, rather than drilling into this thing or trying to infer from a lot of geologic maps of a surface, what was really under there. Because we had this surprise where a lot of the corrugated surfaces in the Atlantic were exposing things other than mantle rocks, though that's what we had initially thought they were. So we just published all this, and here's the references if you want to indulge in these pictures. They're all published. I'll skip this other than to say that I had made a magnetic anomaly map in 2011 that I think shows how magnetics and other potential fields kind of vary in the seafloor setting. The two big results to take away are that Mount Dent, the big area with the Von Dam vent field, has a low velocity anomaly under it in P-wave velocities. So there's a deep, cracking, hot crustal section, as predicted by the geochemistry that we heard from Jeff and others, and we see it geophysically at depth, which is where all those fluid inclusions are feeding in the fluid. So it's very consistent with a P-wave tomography, and that's from Jenny's paper. She's doing her PhD with me on harm. I won't go into details with this other than to point out that our problem is that as you get into these mantle P-wave velocity anomalies, you start getting preciously close to the P-wave velocity for crust. And so as sort of geophysical types, we always worry about this, and that's why sometimes it's nice to have VS shear wave velocities where you can discriminate between, say, serpentinized mantle and more gabbroic rocks. So we weren't able to do that on the main axis, but this is a very important result when we compare these older sections. That's 10 million years of seafloor spreading, 10 million years of seafloor spreading from this axis, right between there where it's very rough and there where it's very smooth. Voila, we have a lot more of this extremely, high VPVS tends to dominate these older regions. So I stuck a red arrow to draw your eye to. So we know that spreading here exhumed a lot of serpentinized mantle, whereas here it's much more patchy in a structurally complicated framework. Okay, I guess now that I've given this talk and getting the nod over here, I realize I did kind of throw a lot of detail at you, but you can sift your way through it and hopefully take some lessons away about what happens in the subsurface. I think when we think about our picture of the ocean floor, we have a very distinctive picture of abyssal hills spread from this rise, this hydrothermal system, but there's more going on than just at the rise and also in these deep rifts of the slower spreading centers. And so as we kind of develop models and use the ocean lithosphere to think about ocean worlds, we might take away some of these more kind of lessons from the subsurface that we've done geologically and geophysically. So I'll leave it at that.
We can take a few questions.
Yeah, Bill.
So you showed a picture of Kilauea. So what about places like Lougheed? Isolated seamounts. This is a completely different environment tectonically. What's the picture? Because that's a real good, I think, analogy.
That's really the analogy to look at. Yeah, actually, I mean, Scott might be best prepared to comment on that, but I mean, in general, the pattern of lava construction is similar between between these specific rise in terms of fissure eruptions and flank deposits. I think the porosity structure of the Hawaiian edifice is much more complex. There's a lot more large-scale porosity variation. The East Pacific Rise is notorious for the kind of sheet flows of massive basalts that don't preserve a lot of porosity, and then intertabular bits that have a lot. That's a great question. I guess I'm just going to punt and say that I think it would be good to get a real, in terms of talking earlier about programmatic strengths, it'd be great if there was a really good flood basalt, Hawaiian basalt volcanologist in the room. Oh wait, there was supposed to be one. But thanks, yeah, let's think about that, yeah.
Nick, is there anything about your data for Mount Dent that allows you to infer the depth of circulation?
Yes, the velocity anomaly is around 5 kilometers down, 4.5, 5 kilometers down, so we would consider that the most porous part of the system. Does that more or less answer?